Hello everyone, hope you guys are doing good. So today we're going to resume the discussion on cam follower mechanisms. And within that, we were designing cam profiles. So the basic idea was that we need to have a cam profile made in a sense that SVAJ diagram indicates that the uh, kinematics corresponding to displacement as well as velocity as well as acceleration and in often cases jerk is properly taken care of. And that was kind of asking us to improve the initial cam profiles. And this is exactly what we're going to resume. We're going to conclude the discussion today. So let's start the discussion. In this continuation, we discussed last time CEP paradigm. This CEP stands for critical extreme points. C stands for critical, E for extreme, and P for points. So as the name suggests, we are only concerned about extreme points and what happens to displacement, velocity, acceleration, and jerk on those points. And we're not interested in what happens in between them. And in order to explore it, we selected one big class of cam profiles, which are called RDFT, which corresponds to rise, dwell, fall, and dwell. So there is going to be uh, two parts where motion is happening in rise and fall, and in between these two, you're going to have phases where there is no motion over there called dwells. So in order to explore that, in order to explore the critical extreme points paradigm, we started from the naive cam design and then we moved on to the simple harmonic motion. And that improved certain attributes corresponding to SVJ diagrams. But that was not perfect. Then we moved on to the cycloidal, where we started from the acceleration profile and then we integrated it to find out uh, velocity and displacement. So that was corresponding to cycloidal paradigm. And then we explored the trapezoidal, in which the modified trapezoidal was also explored. And then we moved on to the modified sinusoid. So you can see that we have gradually gone through this process of improvement where in stepwise fashion we have sought certain attributes to be improved. But at this particular stage, it is advisable to stop there and take one step back and raise this question over here, that is there any other approach other than the approach that we have tried so far? And yes, there is, and that's what we call polynomial functional approach. And this is what we're going to explore in the subsequent slides. So often in life as well, sometimes you need to stop somewhere, take one step back and observe the whole spectrum or scenario in front of you and ask yourself that is there any other way of solving the problems that you're facing. So this is similarly done over here. That polynomial functional approach is going to give you that realization that there is an alternate method, and in certain attributes, in certain fashions, it is going to be much more better than the approach that we have tried so far. So in this continuation, we are going to say that the next discussion is going to be corresponding to that exploration where the polynomial functional approach is going to be explored. And then we're going to obviously make comparisons so that we realize that why we're going to choose one over the other. So that is going to be an interesting analysis phase in order to compare the different paradigms. And then once again, we're going to go back to the original base and we're going to say that, all right, critical extreme points have been taken care of, but what if the path is important as well? So that's what we call CPM paradigm, where a path is critical. So this is critical path motion. So we are no longer very much interested in only the points, but what happens in between these points is also equally important for us. So that exploration is going to be conducted today, and in that we're going to start from the 4 segments, and then we're going to briefly discuss the 2 segment approach. So that's what we're going to cover today as well. And by the way, this corresponds to constant velocity motion. And then there are obviously other paradigms as well. We are not going to explore those today, but this discussion is going to give you a requisite headway uh, into understanding different CPM paradigms. And I remember last time some student raised this question that we should solve a few problems in these lectures as well. So in order to cover those, we're going to cover the graphical approach as well, in addition to the ones that we have studied so far. So this is going to give you the full spectrum of CAM profile designing, and this is the path taken in the subsequent slides. So let's start the discussion. So in polynomial approach, we are going to choose a polynomial, and this polynomial uh, is going to have certain coefficients associated with it. In general form, you can see one polynomial written. Uh, in this case, s is equal to c naught, which is the initial coefficient, which does not have any variable associated with it, plus c1x, and over here x can be uh, in our case theta over beta, which is going to define uh, in a specific user defined beta how the angular displacement is happening, or alternatively this may correspond to t. So when path is important, then you're going to choose this, and when trajectory is important, then you choose generally time dependency. But in this case, we are only focusing on paths, so that's why we're going to restrict ourselves to choosing this as the x. And then you have the higher powers associated with x over here, and it goes on and on. Now it depends on the set of boundary conditions that we're going to define to define the size of this polynomial selected. So this is what we're going to do in the very first approach, corresponding to 3, 4, 5 polynomial. In case of 3, 4, 5 polynomial, we can draw the SVAJ diagram just like this. And as I've just mentioned, that you have to define the boundary conditions. So let's see what are going to be those boundary conditions in our case. So S is over here, V is here, A is here, and then you have the jerk. So this is SVAJ diagram. So in this particular initial scenario, what I'm going to suggest for the moment, that I'm going to have one boundary condition defined right over here, which says that S is going to be 0 when theta, or this theta by beta value is equal to 0. And S is going to become equal to this value, which in our case is going to be h, when beta is achieved. So you have 2 boundary conditions corresponding to S available over here. Then ideally I would suggest that velocity should start from a 0 value. It should start from having no motion or no velocity, and then once the height is achieved, then it should get back to the 0 velocity as well. So these are going to be further 2 boundary conditions added to it. And then in case of acceleration, because we have done quite a lot of discussions corresponding to acceleration, and we said that ideally we should start from a 0 acceleration, and it should reach to the 0 value at the end of the required motion. So in this particular scenario, what I'm suggesting is that you have 3 boundary conditions exactly on this line. You have one over here, second, and the third boundary condition, And similarly, you have three boundary conditions defined over here, which is corresponding to number 4, 5, and 6. So precisely in this case, you have 6 boundary conditions. So now referring back to the polynomial selection, we can obviously define the size of this polynomial. And this is going to be a fifth order polynomial as illustrated right over here. Here it is. Now, in this particular case, you can once again see that when theta is going to be equal to 0, S is going to be equal to 0, V is 0, A is 0, as I've previously mentioned along this line. And when theta becomes equal to beta, S is going to be equal to H, which is the predefined height that we wish to achieve in our rise scenario. V is going to get back to the 0 value, acceleration is 0 once again. So you have, when theta turns out to be equal to beta, you have achieved these further 3 boundary conditions. So in total you have 6 boundary conditions. So this 6 should correspond to the 6 coefficients of the polynomial. So you can now see that in case of polynomial you have C0 as the first coefficient, C1, 3, 4, 5, and 6 coefficients over here. So 6 boundary conditions which are known to you, corresponding to 6 coefficients in the polynomial that you need to find out in order to make this general purpose polynomial mapped onto the specific purpose polynomial corresponding to the rise function in your CAM profile. So this is a very interesting study because you have suggested a fifth order polynomial to define position of the follower. And once the position is known, as we have previously mentioned, we can obviously start from there, take the derivative, and as we have done in previous cases as well, we took the derivative. And when we did that, we found out velocity. And in this particular case, you can readily see what is happening over here. So since C0 is not dependent on theta, so this is going to be taken away in this expression. So there is no C0 term appearing in the velocity expression. Obviously, C1 is going to have an influence coming in from the theta. So when you take the derivative, this is going to be appearing right over here. Then obviously corresponding to the powers of the thetas, you are going to have C2, C3, C4, and C5 terms appearing in the velocity expression. So when you take another derivative, you are going to find out expression for acceleration, and this is exactly what we have achieved right over here. You take another derivative, you are going to find out this as the acceleration. And obviously you can see that starting from the displacement expression, you have gradually found out the 3 most important parameters in this particular CAM profile, which are S, V, A. Now in this particular scenario, you can obviously see these equations, but now since you have specific boundary conditions to be incorporated over here as well, so these are needed to be added in the mix. So you know that at theta is equal to 0, you have these boundary conditions. So let's take the very first one. At theta is equal to 0, S is equal to 0, so this corresponds to right over here. And when you plug in this value of S to be equal to 0 in equation number 1, in this equation, you are going to obviously find out C0 to be equal to 0. Because theta is equal to 0 at that particular case, all the other terms are going to reduce to 0. So that would obviously mean that C0 is necessarily equal to 0 in this case. Similarly, for theta is equal to 0, plug in value um, of boundary condition corresponding to velocity over here in equation number 2, as I've written down over here. You are going to find out C1 over beta to be equal to 0 as well. So since beta is not equal to 0, you know that because this is the tool available to the designer to specify the length of uh, a rise motion. So for that reason, obviously C1 is going to be equal to 0 when you fulfill this boundary condition. And when you plug in the value boundary condition for acceleration in equation number 3, you are going to find out corresponding to this boundary condition that 2c2 by beta squared is also going to be equal to 0. Beta is not equal to 0 actually, because this is under your control. So obviously this would mean that c2 is going to be necessarily 0, which means that you have got these values. So let me encircle them so that you understand or clearly visualize them. So C0 is equal to 0. C1 is also equal to 0. And C2 is also going to be equal to 0. So when you plug in these values back to equation number 1, you would obviously see that this equation number 1 is not going to have those many terms anymore. So these are corresponding to the boundary conditions in the starting phase right over here where I've put the arrow. Now in case of the other set of boundary conditions, where when theta is going to be equal to beta, and you know the boundary conditions, when you plug in those values in, you are going to find out these expressions. So this corresponds to, in your diagram, boundary condition which is over here, and over here. When you plug in these values in equation 1, 2, and 3, you are going to find out one equation to be like this, the other equation to be like this, and the third equation to be like this. Now, in this particular case, you know that you have 3 equations, and obviously you have 3 unknowns, C3, C4, and C5. So obviously you can solve these equations for specific values corresponding to C3, C4, and C5, and when you do that, you get this expression. S is equal to H, and then you have 10 multiplied with theta over beta with cube power, and then you have the other terms in it. So you have one expression corresponding to S appearing right over here when you plug in all those values of C3, C4, and C5 in it. So how we have computed this C3, C4, and C5, this is what we are going to do that in the next slide. So hold on for a moment. So after plugging in the boundary conditions in the polynomial, we are left with 3 equations and 3 unknowns, and that was, if I can rewrite those equations over here, that would be something like H to be equal to C3 plus C4 plus C5, and then you have the other one which is 0 to be equal to 3C3, if I'm not wrong, plus 4C4 plus 5C5, and then you had the other one corresponding to acceleration boundary condition. This turns out to be equal to 0 to be equal to 6C3 plus 12C4 plus 20C5. So let's label them like equation number 1, 2, and 3 over here on this slide. So in order to have 3 unknowns solved for from three equations, you are going to start from somewhere, like from these two equations. So 1 and 2 implies that you have let it be like the first equation multiplied with 3, so this would be something like 3h is equal to 3c3 plus 3c4 plus 3c5, and then you can write down equation number 2 as it is. 0 is equal to 3c3 plus 4c4 plus 5c5. And then you can do the sign reversal over here to cancel the a few terms. So this is obviously cancelled, and you have 3h to be equal to uh, minus c4 minus 2c5. Now similarly, you can take equation number 1 from here, and you can do a similar comparison with or manipulation with equation 3. So this would mean that 1 and 3, when passed through the same process, this would be something like 6h to be equal to 6c3 plus 6c4 plus 6c5 for equation number 1, because we have multiplied it with 6 over there. And then you can write down the equation number 3 as it is. 0 to be equal to 6c3 plus 12c4 plus 20c5. And you can do a similar exercise over here. So this would mean that this term can be cancelled, and you have 6h to be equal to uh, something like minus 6c4 minus 14c5. So I can label this equation as equation number 4 and this as equation number 5. And by the way, I can rewrite this equation 4 like this, like you have c4 to be equal to something like minus 3h minus 2c5. So this would be something like 4 prime, if I may say that. Now you have equation 4 and 5 like two equations and two unknowns, c4 and c5 in it. So you can similarly do the same exercise over there for the simultaneous solution of the equations. So in this particular scenario, you are going to kind of plug in the value of c4 from 4 prime. So plug 4 prime in 5, you would find out the expression for that. So this would something like be 6h is equal to minus 6c4, and c4 is actually 4 prime, so I can write down like minus 3h minus 2c5 in it, minus 14c5. And this would obviously mean that you can solve this expression for c5, because this is the only unknown in it. H is a parameter under your control. You as a designer can specify the value of the rise, so this is controlled by H, so you need not to worry about that. You only have got this coefficient to take care of. So when you plug these values in, this would turn out to be 6h is equal to something like 18h plus 12c5 minus 14c5. This would mean that c5 is equal to something like minus 12h by, I suppose, minus 2. So this would mean that this is equal to 6h. Now you have the value of c5 known. You can plug this value in expression 4 prime, and this would mean that plug this value in 4 prime, and this would mean that you have the value for c4 is going to be minus 3h minus 2 into 6h. So this would mean that c4 is equal to something like minus 15h, if I'm not wrong. So this is the other value, and C5 we have just computed to be equal to 6h. So I'm going to rewrite that over here. So now you have got C4 and C5 terms available. Plug these two values uh, in one of the initial expressions, like equation number 1 can be used. So when I do that, this would mean that h is equal to C3 minus 15h plus 6h. So this would mean that C3 turns out to be equal to something like, yeah, I suppose 10h. So this is the third unknown coefficient available for you. So now you have got in this simultaneous solution of the equations the solution, and this would mean that now you have got the coefficients specified corresponding to your equation. So now you can see that C3 is appearing right over here, and C4 is appearing right over here, and C6 is appearing over here, and H is taken common out of this expression, so that's automatically taken care of, and the rest of the stuff is quite obvious. It is similar to the expression that you have seen in the last slide. So in this realization, you can now see that the polynomial corresponding to position of the follower has been specified, and this contains the powers of 3, 4, and 5, and that's why this is called 3, 4, 5 polynomial in the initial discussion that we had. So this is for 3, 4, 5 polynomial. So in case of 3, 4, 5 polynomial, you have seen that we have used 6 boundary conditions. In those 6 boundary conditions, 2 were corresponding to position, 2 for velocity, and 2 more for acceleration. So someone may raise this question that what if we wish to define 2 more boundary conditions for jerk as well? And that's what precisely happens in order to have further improvement done in case of cam profiles. So let's see this scenario. Possibly this is going to be the situation. Let's try to find out what is happening over here. So the 2 boundary conditions corresponding to S are over here highlighted. Similarly, for velocity, you can see that velocity starts from 0. It goes all the way back to 0 after completing the rise stroke. And then for acceleration, it starts from 0 and it goes back to 0 as well. So that when you have rise dwell, fall dwell, the other kind of phases added to the system, it does not create problems as well. So now for the very first time in case of J, we have added 0 initial condition for the starting value and 0 once again jerk value once the motion has been completed, once the rise has been completed. So this is needed to be incorporated. So now you can obviously see that on this line you have 1, 2, 3, and 4 boundary conditions, and corresponding to this extreme you have 5, 6, 7, and 8 boundary conditions as well. So when you have 8 boundary conditions, obviously you are going to use 7th order polynomial in your case. And this is exactly what we are going to do. And once we do that and follow the same procedure that we have followed over here to find the unknown coefficients for that, we are going to find out this as the expression for S. Now over here you can see something like this, that S is equal to H multiplied with this term, this, and this, and these correspond to uh, order 4, 5, 6, and 7. That's why it is called 4, 5, 6, 7 polynomial, because of the structure of this polynomial. But the other thing that you can kind of readily identify, that the coefficients of 3, 4, 5 polynomials were a bit smaller in their values as compared to the coefficients over here. So this 35 seems a bit bigger, or quite a bit bigger than 10 over here. This 84 seems significantly higher than this value, and so on and so forth. So in case of 4, 5, 6, 7 polynomial, the good thing is that you can specify boundary conditions for jerk, which is going to make it much nicer, and you are not going to find out discontinuities or spikes in it, or some random abrupt changes. But on the other side, the downside is that the coefficient values are a bit bigger. So it would mean that eventually, in case of velocity and acceleration as well, you are going to expect a bit higher values for velocity and acceleration. So this is a bit of concern when we add something order to the polynomial. But the good side is that you have a continuous jerk. So you get some advantages and you get some disadvantages as well, as is the case in generally whenever you make some engineering decisions. There's this famous saying that there's no free lunch. When you try to add some good things in your situation, you are going to add some negative aspects added to that by design. So it is similar scenario over here, but I can say with confidence that in terms of it SVAJ profile, it is much smoother, much better as compared to 3, 4, 5 polynomial. So you have seen in these cases where we have selected polynomials that you start from a general purpose polynomial, and depending upon the boundary conditions, you are going to specify the coefficients. And this particular procedure is going to be repeated whether you opt for 3, 4, 5 polynomial or 4, 5, 6, and 7 polynomial. Okay, now let's compare all these different profiles together. In this critical extreme points paradigm, we have covered quite a few different variants. We have seen the simple harmonic motion, we have seen the cycloidal profiles and trapezoidals and modified trapezoidals, and then recently the polynomial approach as well. So it would be appropriate now to compare how the jerk is behaving vis-a-vis each other, and how the acceleration, velocity, and position is going to have their profiles generated when we opt for a particular profile over the other. So this would give us that deeper insight that when you get some benefit from a particular paradigm in a particular kinematic approach, what is going to be the positive side of it and what is going to be the negative side of it. So let's compare them together. So at this particular stage, I would raise this question for acceleration comparison, that what is ideal in case of acceleration. And I would invite you to recall the very simple, straightforward expression that you have seen so many times. F is equal to ma. Now in case of follower being governed by the cam motion, you can see that follower is going to have a specific mass. So acceleration number, if it is a big number, it would mean that the force requirement is big as well. And if acceleration is not that big, it would mean that the force to run or move the follower is going to be lower as well. So in this continuation, ideal scenario would be to find out a motion profile which does not give you higher accelerations. So in this particular context, see what is happening over here and find out what is the profile for which the acceleration is lowest. And I can readily see the modified trapezoid, which is right over here, indicating that the acceleration goes maximum like over here. It rises up, obviously, it falls down, obviously, as is the case for the other profiles. But the maximum value of acceleration is not that big as compared to the others. So obviously, in that scenario, modified trapezoid is going to be ideally suited for acceleration. Uh, the other candidate can be like modified sine. You can see that happening over here on this profile. It goes up and then falls down. So this value corresponds to the maximum value of acceleration exhibited by modified sine. It is not that good as modified trapezoid, but as compared to the other approaches, this is behaving very well. And similarly, a close by candidate can be uh, the 3, 4, 5 polynomial right over here, which goes somewhere over here, very close to the modified sine acceleration. So with this realization, I can readily see that acceleration should not be that big a number. And in this context, modified trapezoid, modified sine, and 3, 4, 5 polynomial gives us better acceleration values. Uh, but having said that, you can obviously realize that once the acceleration is ideally suited, we need to have the other kinematic parameters to be compared as well. For example, jerk and the velocity and the displacement is also needed to be compared as well. So a snapshot right over here may not give you the complete picture, but if you only consider acceleration, you have selected a few good candidates. And on top of that, you can also realize that the polynomial that we have just uh, uh, solved last time, that is corresponding to 4, 5, 6, 7 polynomial. And we said over there that the kinematic values are going to be a bit higher because the coefficient values turn out to be a bit higher. So you can see readily like that is validated, that observation is validated over here as well. So not only this acceleration comparison gives you the realization of in terms of comparison, but it also gives you realization that what is kind of unwanted or less than ideal situation that is needed to be taken care of for a particular selected motion profile. In case of jerk as well, it is appropriate to identify what is going to be the ideal scenario. So if jerk is higher, it would mean that there is some adversarial experience given to the follower. It tries to change in a very fast fashion, which would induce vibrations. So higher value for jerk would mean that there is a possibility of vibrations in it. An abrupt change, like from the dwell to the rise and from fall to the dwell, and whenever there is this transition, the discontinuity is also going to have um, uh, a manifestation in terms of vibrations. So for that reason, we need to identify or compare these motion profiles with each other. So with this realization that higher value of jerk is needed to be avoided and discontinuity is needed to be avoided, you can see the different curves plotted one over each other. And in that you can obviously see that the best suited one turns out to be the 4, 5, 6, 7 polynomial that we have kind of recently solved. It starts from zero value right over there. It goes up and goes all the way somewhere over here to this value, and then it falls down and goes to the other side. So among the other curves, you can have a comparison that the other curves are starting from some other finite values, which can be problemsome. So 4, 5, 6, 7 polynomial is something which is uh, unique in a sense that it starts from a zero value of the jerk. So there is no discontinuity in that sense over here, which would mean that it is not going to have those many induced vibrations in the in the follower motion. But as far as the maximum value is concerned, you can see that cycloidal uh, profile is giving you, in terms of comparison in terms of maximum values, it gives you the lowermost values over here. So cycloidal can also be a candidate as well. The problem with the cycloidal is that it does not uh, start from a zero value. But having said that, cycloidal and 4, 5, 6, 7 polynomials can be suitable candidates. The other candidates, like modified sine or modified trapezoid, that were performing very well in terms of acceleration analysis, they're not performing that well over here. So this is something like a problematic area over here, that although we have observed these to be performing really well in case of acceleration comparison, but they are no longer a very good choice when you wish to reduce the induced vibrations in cam follower motion. So with this realization that you have got a jerk comparison over here, giving you some deeper insights, which also gives you that realization that on the basis of acceleration, which a profile is performing really well, may not be behaving very well in case of jerk comparison. So you need to kind of strike a balance between the selected kinematic parameters to make the final decision. So in a nutshell, cycloidal as well as 4, 5, 6, 7 polynomial performs well, but having said that, you need to be careful about the other comparisons as well, in terms of acceleration and velocity and position, etc. So let's move on. So in case of velocity as well, uh, let's find out what is going to be the ideal scenario. So for a single mass having only one velocity component, you can recall that kinetic energy was something like half mv squared. So just like for the sake of giving you a base expression over here, I've written down like this. So if you have velocity to be higher, you can identify that the kinetic energy is going to be higher as well. So you wish this value of kinetic energy to be not exceeding that much. So that would be the ideal scenario. So in this context, you can identify and compare different curves with each other. And with this realization that we wish to have low velocity achieved, and that would be suitable, I can identify that the modified sine is the best suited one. And the worst in our case is 4, 5, 6, 7 polynomial, and the reason is already identified when we solved for that expression, and we found out that the coefficients were bigger numbers. So in case of velocity, you can readily identify that on similar grounds you can make comparisons. Modified sine turns out to be the best one, followed by 3, 4, 5 polynomial, and the one which is adversarial is 4, 5, 6, 7 polynomial. And this is kind of also highlighted once again that obviously when you are going to have a comparison, you would obviously observe that uh, all the parameters, kinematic parameters of acceleration, jerk, velocity, and position are compared when you choose a particular profile. However, in case of position, you would observe that there is only a minute difference between the selected curves, and this is a very uh, good observation that you can make, that a change incorporated in position, a very little change incorporated in position is going to result in a big change exhibited in terms of acceleration, velocity, as well as in jerk. So over here you can see that there is no big difference, but in case of the corresponding curves in velocity, acceleration, and jerk, you have already observed that there are quite a few big differences. Make this realization that a curve which seemingly is kind of similar uh, uh, to to the benchmark curve may not be as suitable when you compare the other kinematic parameters. So that is why it is important sometimes to compare these values side by side with each other. So in this case, you can see that the maximum velocity and the maximum acceleration and the maximum jerk are being compared alongside each other so that you may reach a reasonable compromise or a good compromise. So in case of constant acceleration cam profile, you can see that the maximum jerk is unacceptable, and similarly for harmonic displacement as well. So with this realization that these are unacceptable, you can take them out from the comparison. You can see that in case of 4, 5, 6 polynomial over here, the jerk values and the acceleration values are much higher as compared to the others. So these are going to give you some problems when you consider the acceleration and jerk, and correspondingly the force requirement as well as the induced vibrations. So with this realization that you have got these kind of adversarial values over here, you can get to the middle of these comparisons and you can see that what is happening over here. So potentially you can see that a good compromise is reached over here in case of 3, 4, 5 polynomial displacement, where you can have kind of a trade-off between the maximum values corresponding to velocity, acceleration, jerk. So sometimes it would be advisable to compare these velocity, acceleration, jerk values side by side with each other in order to reach to a final conclusion. So all the discussion that we have had was corresponding to RDFD design, but this was only one set of possibilities, uh, one kind of cam profiles. Sometimes you may not have double dwells in the cam profiles. You may have a single dwell. Sometimes you may not even have a dwell. It simply rises up and then it falls down. So there is a little section in your book I'll advise you to read yourself, and this is going to broaden your horizon in terms of cam designs. So do read it. So let's take a short break and we're going to resume the next section after a couple of minutes.